Okay, hello, welcome back to making a synthesizer in C. This is episode 6. This is actually take 2 of episode 6, because the last time I tried to record this, I mucked up the audio settings, there was no audio. I just had a curry, so I had some chutney on my cheek. It was a disaster. So there is some stuff I did offline, so I'll just quickly run through what I added. So I fixed the drop-down boxes. All we did was we've got this loop where we're looping over each panel in the UI, but we moved the actual drop downs into a second pass. We then loop over again over that and then draw the drop downs, and that's how you fix that problem. So yeah, we just do it in 2 passes. I've also added a shape parameter to the UI. So if I come to the square wave, you notice it's got this third slider here, and this can be used to change the this is called the duty cycle, so how much of it is positive to the ratio of how much of it's in the negative space, and you can see that slightly changes the tonality. So if it's sort of even, it's got a richer, fuller sound, and as you make the ratio more extreme, it becomes a tinier. Can you hear that? It's much more tinier. So that again was pretty simple. So we added a shape parameter and we added a duty cycle to the square wave. So let me show you that. If I come to square wave, where is our square shape? So we come to our square wave, you can see we've added a new parameter to the oscillator called shape parameter. And instead of checking if our phase is below 0.5, if our phase is sort of below the half point, we're now checking if it's below the duty cycle parameter. And we had to also tweak our band limited ripple a little bit, where we have to do modulo the phase plus 1 minus the duty cycle, because I had the issue where it was putting the ripple at the wrong end. So if you were to move the duty cycle to the left, the ripple was moving to the right, so that's why I had to do 1 minus the duty cycle here. So we come to our oscillator type here. Oscillator, you can see I've added this shape parameter. I've labeled it 0 because we might want to add extra shape parameters to our oscillator. And the reason I've just calling it shape parameter is we've added a new type of wave shape. Let me come back to this, and I'm calling this the rounded square. So the rounded square starts off as a sine wave, but as you change the shape parameter, it becomes more like a square wave. And in between, you can sort of round off those edges. It's easy if I stretch this a bit. So if I come to our rounded square shape, you can see here it's not too complicated. It's this function here where we're taking the shape parameter, we're manipulating it, we're taking the base, and then we're doing sine. Let's see if I can find. Let me explain to you. I'll bring out the graphing calculator. I've got it already set up here. So let me go to this view. So here we are. This is the formula for creating a rounded square wave. I think this needs to be 2 and then minus 1. Yeah, sorry, that's correct. So yeah, you can see this is a formula for creating the rounded square wave. It's all looking good. So it's the value of s to the power of s times the sine of our sort of oscillator, and then there's a bit of plus 1 minus 1 to get it centered around the 0 line. and are they going up to 1 and -1? It's basically what all these constants are doing here. So that's all looking good. Nope, don't need to save that. Okay, just make sure everything's good. Right, so that's everything we've done so far. So I can get rid of these notes. So what I want to do today is the ability to play notes. So like a keyboard. So how can we do this? Probably the simplest way is if we come to, sorry, yeah, where do we update? So we've got our handle audio stream here. Oh yeah, I think I cleaned up, I refactored a little bit. I've changed this now into an oscillator array, which is just oscillator and the size t count. Yep, let's come down again, back to our handle audio stream. So really what we want to do is set we want to override the frequency that we're setting. At the moment, we're just setting the frequency manually. Like with this. But really, we want to be able to like set the frequency based on what note we hit on our keyboard. So we can do that in here, where we're sort of looping through each, we're applying, so what's this make oscillator, let's go to that. Oscillator is just returning a new oscillator from the array. Draw UI at the end of this. So it's really here where we set the frequency. We kind of, what we want to do is say our float note frequency is 4/4. Let's say it's A. Well, let's just try something. So is key down, I believe it's called, and then we can put in like key A, right? And then we can just say is A down, and then we'll do 440, and if not, we'll play note C. So let's see if I can find a table of note frequencies. Here we go. Whoop. So here's a list of our note frequencies. So if we find 440, A4, here we go. Note A4 is 440. So what's C4? C4 is this number here, this frequency here, 261.63. So we can paste that in here. And then we just, where we're saying the frequency here, instead of doing that, we're going to say osfric frequency equals the note frequency. So that's good. Close that. So really what's going on here? So now we're talking about, basically now we're talking about music theory. On the Western note scale, there are 12 keys in an octave. I can show you, I've got a, let me come back to this view. So here I've got a MIDI keyboard. And you can see that actually there's a load of notes in here, but the only notes you sort of have to worry about is, can you see that this is C, and from here to here, all the notes in between here is an octave. And then basically if you imagine if this was a really big piano where it goes on for longer, it just repeats the notes again, but 1 octave higher in frequency. And so what is an octave? Basically it's double, to go up an octave, so 440 equals A, you see in here, 440 equals, can you see that? A440 equals note A4. So this is the 4th A note on the piano. If we go an octave higher, then we go to A5. And look, it's A80. It's double what the lower octave is. That's how octaves work. Each octave doubles the frequency. So if you look at C4, 261.63, let's validate this. What I can do, times 2 is 523.26. So let's validate that. Let's go to C5, 523. All right, there's some precision, but yeah, just off by 100th. So what we can do is we can say, like, all right, let's say A4 equals 440. That's going to be our bass note. And then we'll say our note. So if our note is 0, then we're going to play A4. If our note is 12, or is it 11? If our note is 11, we're going to play A5. So really, our flow A5 equals A80. So this would be note 0, this would be note 11. So basically, we then, to get all the other notes in between these two, we need to divide that space into 12. So what I can do is but just use the number keys for now. So really, what I want to say is key down, key 1. Is that a key? So the numbers along the top key, plus I. So I'm going to do this in a loop. How many keys we want? Key 9 minus key 1. And then we'll just say our int key index equals 0. We'll start from -1. And then we'll say if that key is down, press the wrong button, key index equals I, or key 1 plus I. Actually no, we can say this is 0. And then break. And then what we can then say is our float note frequency is 0 by default. And then we can say if key index is greater than or equal to key 1. Our note frequency is equal to, let me get our A4 so if it's 11, if our, let's just say our key relative index is equal to the key index minus key 1. So now it's, so if key relative index is 11, we want to times this by 2. So we could say, we can make this a float, right? We could say float times key relative index so I am going to count from 1 to 12, so I'm just going to do 1 plus key index minus that, and then key relative. Then we can call this the semitone, because that's what each of the 12 notes is called. They're called a semitone. So I can do semitone times. So this is wrong, and I can explain why it's wrong in a bit. Oh, it would have to be semitone divided by 12. Because then when we get to 12, this would be 12 divided by 12 would be 1 times 2, so it would be times 2. But yeah, you can see this is wrong, because if you want to play just note A4 itself, we need this to become 1. And if this is 1, then we get 1 divided by 112 times 2, which is obviously not 1. So we're going to have to use some other function to calculate this, but I can show you how this works. So let's get our sine wave. The 9 isn't working, and that's because we actually want to do key greater than or equal to. So it's playing some notes, but it's not playing proper semitones. So we now need to figure out how do we actually calculate the frequency. So I believe the function we might need to use is power or exponential. So let's have a look at this. Formula to calculate frequency of semitone. So the frequency as a semitone, distance from A4, for notes that lies n semitones higher or negative n semitones lower from A4, the frequency f of n is 2 to the power of n over 12 times 440. Conversely, one can obtain, can you see that? Let me make this bigger. Yep, so the frequency, the formula here is this one, 2 to the power of n divided by 12 times our base note, which is A4. Conversely, one can obtain n, so you can go from the frequency back to the number of semitone by doing 12 times log 2, the frequency, divided by 440. So we want these two functions. We want this one, and we want this one. So what I'll do is I'll make a function for these. Put these somewhere up here, and we'll just say yeah, static float we'll call this get frequency for semitone. We're also going to define our base note frequency. That's going to be 440. We'll do that. So this is going to ask for the semitone, which actually I'm going to pass it in as a float. So remember our so what we need to do is we need to return, so this is to the power of so 2, so we need to turn 2f to the power of our semitone divided by 12 times our base note frequency. Now we want to do get semitone for frequency. And come back here, this was our function. So that needs to do 12 times log 2, I don't know if that exists. Let's check if C log 2f. Yep, log 2f exists. So log 2f of our frequency divided by our base note frequency. Alright, so let's come back down to our function down here. So we can get rid of this, and get rid of this, get rid of that. And so now our note frequency is just going to be get frequency for semitone, and that's going to be the semitone. Undefined symbol log 2f. I guess it doesn't have that. We do have math. Let me just make sure. Why can't it find that? Because we are including math.h. The standard are in a different library. Okay, so we need to come to our build, and then I believe we need to link to just a library called M. Let's see if this works. Library M not found. Microsoft might have it. Why can't it find it? Oh. Oh wow, so we have to guess we have to roll our own. Well, that's annoying. Okay. We're gonna just do floats. So this is gonna be log f. Clean this up a bit. And then we need to get rid of that. Here we go. There we go, that's sounding good. Let's add in our square wave with the shape. All right, so got that working, but using the computer keyboard, my typing keyboard, as a musical instrument isn't the best experience. What I really want to do is use my little MIDI keyboard. So that's what we're going to do now. I'm going to implement some MIDI input. So how am I going to do this? So what I'm going to do is let me close some of these windows and get, so I had some, if I open my resources, so here's the documentation for opening MIDI input in Windows. So this won't be this won't be cross-platform. We're just going to do Windows MIDI input for now. So we're going to be using the Windows API, which, to be honest, is horrible to use, but hey ho. what can you do? So I did have a brief overview of this before, and I also managed to find a little sample on GitHub for sort of opening MIDI devices. So we can use both of this MIDI reference on the Windows documentation and this sample to do this kind of thing. So the first thing I think we need to do is, again, let me increase the size of this and the size of this. So let me is get this function here, MIDI in get dev caps, which I believe stands for MIDI input get device capabilities. So we need to figure out what MIDI devices do we have connected to our computer, and to do that we need to know how many MIDI devices are connected to our computer. So I believe that's called this one, MIDI in get num devices, which returns an int. So let's do that. So we're going to create a new function. For now, we'll do this separate from our synth, and then we'll merge it once we know it's working. So I'm going to call this MIDI.c. So first thing, I'm just going to include standard I/O. So we've got the print. What else are we going to include? If we come back to this and look at what they include in the sample program, they include Windows.h. So we're going to include Windows.h, and they also include something called the system.h, and I believe here stands for multimedia. So this is the Windows multimedia system for handling things like MIDI input and audio. We don't need to link, so we come to our build file. It's already linked to the Windows multimedia library. Now we are going to have to make another one of these. Oh, are we? You know what? For now, I'm just going to say build the MIDI, output MIDI, and don't auto run it for now. I know it's called build then run, but we're not going to auto run it because this is just going to be a. Maybe I shouldn't do this. All right, change it. What we'll do is we'll copy this, and we'll create a new file called build.bat. Paste that. I'm not going to run it. It's not going to be a GUI. We're just going to do it as a console line application. We're not going to need Raylib. We just need all that. We're not going to need OpenGL. Oh. But I will include all that, and then this becomes MIDI and MIDI.exe. And then, so if we come back to our MIDI, another thing we're going to need is include, this is con.io.h. I believe this is console input output. So this is just so it can like detect when we press a key, and we can like quit the console application. So let's first have a look. We're going to need our main function. So we are going to have the int argc char argb. So that's if we want to do console, and I'm just going to return 0. And then I'm just going to do, this is our MIDI test. Right. So if I open a command prompt, if I come to, let me just go to the folder, which is dev. Here's a command prompt, and then what we're going to do is build MIDI.bat, and then if we just run MIDI, here we go, we can see MIDI test. I don't know if there's any way to, oh there is. Wait, there's bigger in font size. Cool, so I'll put that down there for now, and then I can quickly switch between it. Let's come back to our function here. So what we're going to have to do is call this function MIDI in get num devices. Now, Windows, it loves to use like all these their own type names and these big caps. So I'm going to type def these to some nicer types. So UN is an unsigned int. I'm just going to call that U32. And then all the other stuff, type def, unsigned char, that's we can call that U8, type def, unsigned, short, that's a U16, type def, that's a U64. So this is going to return U32. I'm going to call this num MIDI devices. And then we can loop over. So we can do U32 device ID equals 0. Device ID is less than num MIDI devices, device ID plus plus. And then we need to now look for the function which was MIDI in get depth caps. So you pass in the device ID, it returns this crazy thing, which is a pointer to a structure. So if we have a look at this, the structure here, MIDI caps. The only thing really we care about in this is this. Like I said, the Windows API is just horrible. But yeah, this P name, that's the name of the device. And then the size and bytes of the MIDI cap structure. So. And then it returns an MM result, which I believe, again, is a U32. So what we'll do is result equals, let's do this. So it takes in our device ID. And then it's going to take in, I'm going to type def, what was it called? LP MIDI in caps. That's just going to be called our MIDI capas, MIDI info, MIDI device info. So I'm going to call MIDI device info, and then I think you just need to pass in a pointer to that, and then you need to give it the size of MIDI device info. And then what we can say is if the result is equal to, and if we come back to this window, it said returns MMSys no error if successful or an error otherwise. So I'll say if it's non-equal, don't do that, to MMSys no error, then we're going to printf could not get MIDI device info. Return 0. Otherwise, we're going to printf MIDI device, and we're going to pass in the info.scp name. Right, let's give this a go. Assignment from incompatible pointer type, error struct 2128. So let's have a look at the sample program, see how they do it. They get the num devices. Oh, they don't have a print MIDI devices. Get num devices. They loop over it. Caps, MIDI in caps. Oh, so they do MIDI in caps. Okay. Let's try that. There we go, MIDI device LPK25, and you can actually see, if I show this up on the camera, although I don't know if the camera's flipped the text, that's the name of my device. Cool. So that works. So now we need to tell Windows to go ahead and start talking to that device. So we'll just say our selected device ID is going to be 0 for now. And then let's have a look at the documentation again. What we're going to need to do is call MIDI in open. That opens a MIDI device. So let's have a look at what this. It needs a pointer. So this is, we're not passing something in. This is going to pass as a handle back out. Pointer to a MIDI in handle. It takes a device ID, so that's the index to the devices. We're just doing the first one, which is 0. Pointer to a callback function, so that's going to be a function that gets called every time a MIDI event comes through. I believe DW instance, user instance, so that's if we want to pass just our own data to that callback function. FDW open, callback flag for opening device, optionally status flag. So I believe we just want to pass in this callback function value to tell the API that, yeah, we're setting a callback function. And then it returns the usual error codes. So let's go ahead and do this. Copy that. And so what we'll do here is say MIDI device info. We'll call this our MIDI handle. So this is going to take in a pointer to our MIDI handle. It's going to take in the selected device ID. We need to take in our, so add callback here. So it needs to take in a function pointer to our callback. We're not going to pass it any data for now, and we're going to pass it, what was it called again? Callback function. Callback function. And then that's going to return a result. And again, we're going to do the same thing. If result does not equal BEP, then we'll printf could not open MIDI device. We'll pass in the index, selected device ID, and then we'll just return 0. So once we've done that, we then need to tell it to start. So we have two functions here, MIDI start, MIDI stop. So to actually, we've opened it, now we need to start listening to it. So that's pretty simple. We just pass in the handle, MIDI in start, and then again, returns results. So we'll say result, MIDI in start, and we'll pass in that MIDI handle. Again, we'll say result is not equal assist no error. Printf could not start MIDI device. We'll just quit. And then this is where we're going to do our loop. Our application loop goes here, and then we need to tell it to stop. So MIDI in stop, again, takes in our MIDI handle, I believe. Let's just double check that. Oops. Yeah. And then once we call stop, we also need to close. So that's MIDI in close, which again takes our handle. So we'll copy this. We'll say could not stop for whatever reason, and then result. MIDI in close, MIDI handle, and then we'll say could not close. Hold on. Very good, very good. So now we need to add in our callback. So if we come back to this, we look for our MIDI in open, and you see it pointed to a callback function, a thread identifier or handle. So for information on the callback function, see MIDI in proc, MIDI in callback function. So this is going to be our function signature for our callback. So it's going to give us the MIDI handle, the MIDI device info. I believe W message here, MIDI input message, that's the type of message. This instance will be our that data we can pass in ourselves. So the one below the callback is the instance data. So that's just any user data we want to pass the callback. And then I believe the actual MIDI message exists in these two parameters here, which is a D word. So I believe that's a same as a uint. It's a unsigned 32-bit int, right? 4 bytes. Yep. So we'll copy the signature and we'll come here and we'll call this our MIDI callback, or we'll call this our MIDI handler. We do have to leave this callback keyword. Windows expects that. So h MIDI in. So we're going to type left that. So that's our h MIDI in. That's our MIDI handle. So our MIDI handle MIDI. This will take a U32. We'll call this the message type. Again, this is our, I believe it's a pointer, so this is our instance. I'll call this user data. And then it takes the param1 and param2. So then what we need to do is say switch on message type. And we need to figure out what our cases are. the message type. Let's have a look. MIM data. I don't know. Where's the list? Like the list of MIDI messages. MIDI messages. Here we go. So this is all the possible message types that can come in. I'm guessing this is like if it disconnects, we've got an error when we open, blah blah blah. But the most important one is data. So this is the MIDI input. So let's copy that. So if it's data, then here we go. So param1 becomes our MIDI message, and param2 becomes the timestamp. So we'll say U32 MIDI message equals param1, MIDI timestamp is param2. So the MIDI message is packed into a double word as follows. So this doesn't actually explain what a MIDI message looks like. So I'm gonna look for MIDI data type, I don't know. And let me make this nice and big. There we go. A MIDI message is made up of an 8-bit status byte, which is generally followed by 1 or 2 data bytes. There are a number of different types of MIDI messages. At the highest level, MIDI messages are classified as being either channel messages or system messages. Channel messages may be further classified. A channel voice message. So data bytes, D7 to D0. So you got a note off event, a note on event, key pressure, control change. I'm trying to understand this. Status. So the first byte is right, I think I understand to read this. So this is the first byte, this is the second byte, this is the third byte, and I believe the fourth byte, because don't forget it's a 4-byte message, is unused. So if the first byte is 1000 plus some extra data, which we can ignore for now, then that's a note off event. If it's 1001 plus extra data, it's a note on event. And then in the second byte, we've got the key number, which is, you know, the number of the note we're playing. And then in the third byte, we've got the velocity, and that's how hard you press the key, if you want it louder or softer. So an easy way to do this is to use a union. So the way a union works, I'll call this a MIDI message, it's a bit like a struct where you can have multiple fields, but whereas a struct, it will lay out in memory each field one after another, it just looks for, in a union, the compiler will look for the biggest type in that list, and that will be the size of a union, which means you can have multiple data types in there, and you can reinterpret that data as any one of those types. So we know the actual message is a U32, but then we can do it also as an array. We can represent that same data as an array of bytes. So it makes it very easy to index into each byte of that U32. And you know, that makes sense because 32 divided by 8 is 4. So what we can then say is the MIDI message message equals param1, and then we can say like U8 the MIDI event is message data 0. The MIDI note is the second byte, and the MIDI velocity is the third byte. And then we're going to print this. I'm going to do printf percentage d percentage d. I'll do like event note and velocity. And then I'm not going to do backslash that. I'm going to do at the very beginning of it \r, I think. I'll show you what that does in a bit. So that's going to take in our MIDI event, MIDI note, and MIDI velocity. And now we need to have a loop, our application loop. And so that's just going to be a while one, an infinite loop. We need to just let this program loop, and we'll quit if we press the Q key for quit. So char key char equals, I believe it's called get char, get ch is get. It's not getch. It's short for get char, the character that has been pressed on the keyboard. Then we can just say if key char equals a character Q, we'll break out of the loop, and that'll come here and it'll quit everything. I believe that's it. So we can build this. We got an error, 29. Expected, oh, did we forget to? What am I looking at here? Can we not do that? Oh. Yeah, that's right. Where are we missing a semicolon? Case, data, semicolon, 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 semicolon. That's meant to have a semicolon. I'm confused. I'm missing, like, it's a syntax error somewhere and I can't see it. Assignment 65. Well, we got an error. Oh yeah, we actually need to pass in the, so it's MIDI handler. So we can get rid of that. $76. I feel like we really mucked up a... This is right. I mean, you don't have to put it, but you can do the same here. Doesn't like... Oh, this needs to be a MIDI handle. I'll just talk about the MIDI. And then... $67. Oh, that's just a warning. Assignment makes integer from pointer without a cast. Can that just be that? Oh, that needs to become U32, right? All right, it's running. But I'm pressing the keys and I'm not getting anything. Why is that? Let me just make sure that, put that back. Yeah, nothing yet. So, I need to now put this back and try and figure out what the problem with that was. So let's do some binary search. So that should be okay, right? Case MIM data break. Yep. So let's try how I had it before, where I put it in a block. That should work. Yep. Let's move this in. So it's this. Oh, I think that's why. Yeah, I have to put it in a braces because obviously I'm constructing a union. I'm gonna get rid of this because that's not needed. Okay, so I don't know why I'm doing it this way. It would have been so much quicker to just like copy it or. So let's build that. Make sure I do this properly. This becomes U32. And then do MIDI, and now I'm gonna get my MIDI device and whee! So, if I press C in the middle, note 60, the A before it, 57. If I go one semitone up, I should see 61. And if I press lightly, we get a low velocity. If I press hard, and then in between, I get different velocity values. When I let go, we get event 128. So I'm guessing 128 is note off, and when I press a key, I get 144, so that must be note on. So I'll make a note of these. 144, 128. So we'll say I've already forgotten. 128 equals note off, and 144 equals note on. Let me just double check that. 144 equals note on, 128 equals note off. Yeah, got that right. So, great. We could probably start making use of this user data. So I could create a new structure. And call this a MIDI and then we can just use like pools, do we? Is on note and U8 velocity. No, I'll do MIDI key. And then we're just going to have, as a global, current key. And then this can pass in a pointer to current key. Again, I think it expects it as a U32. And then we can get that MIDI key key equals MIDI key user data. And then we can say key dot is on is equal to if message. You know what? Change that. If MIDI event equals, I'm going to define these to key on. We'll define these in a bit. Key dot is on equals true. Else if MIDI event equals key off, key is on equals false. And then we can just say if it's key on, this is where we'll set the key dot note is equal to message dot data 1, and the key dot velocity is equal to message data 2. So we'll define these up here. What did I just do? Right. We don't need these, and then I'll take that. And we can actually just print that in our loop. So we can say, on. So that will be our current key dot is on. We'll say yes, otherwise we'll say no. Current key dot note and current key dot velocity. Let's give this a go. True undeclared. Oh yeah. We'll just say 1 and 0 for now. How's that working? Build MIDI doesn't seem to like to. Oh, is that because this blocks? Oh yeah. I have to like hold a key down on the keyboard so it doesn't block. But yeah, so pressing down a key now, I'm going to let go. I'm going to press down a different key, I'm going to let go. So at the moment, what we got here is a monophonic. So I can only press one key at a time. It doesn't handle me like doing a chord of keys. In fact, if I hold one note down, say I hold down C, and then I press A, it just updates that. And if I release A while still holding C, it now thinks I'm not holding any note. So to handle polyphonic, really what we're going to need is a list of keys. So let's say we wanted to handle up to 16. I'm not going to play like a... Yeah, we'll do 16. I'll call this polyphonic count. And then we'll do static current keys count. And that's how many actual keys. We might not actually need this line. Or maybe we will. So when we get a key on press, what we'll do is we'll get a MIDI key. It's going to be current keys plus current keys count plus plus. So we don't need this anymore. Actually, this will be keys, and it's a said I'm going to do a different struct for this, and that's just going to be a keys and then count. And current keys will just equal that. And then instead of passing in the current key, it's current keys. Call that MIDI key array. And this would be MIDI key array. Keys. So it'll be I call this data. So it'll be keys.data plus keys. What we need to do, because it's a pointer, count plus plus, and that will give us a key. And then when we get note off, I think there's a better way to do this. We don't need for now, we'll just say the count is already polyphonic. And then we're just, when we're trying to find a key, what we can do is do like for I is less than keys count I plus plus, and then we'll just say if keys dot data I is on false. So we'll just set key to the first key. That's off. And then when the key is set to off, MIDI key, and then we also need to say if, so MIDI key equals 0 by default, if key then we set it. We'll say the note is equal to message data 1. So we need to say and keys.data I.note equals note. Right? So we need to find a key that's on that's got the same note when the key off comes through. And we'll set the key to that, and we'll say if key key is on equals false. And then what I'm going to do is hoist these out. UA velocity equal, yeah, I'll put these back here. So we'll just say that's equal to note. Velocity. Oh, I'm not using the same keys on false. Cool. So then we need to print these out. So yeah. What's the nicest way to print this? I'm just going to do the first three notes. Nope. Percentage D and I know this is a horrible way to do it, but and then I'll just do current keys data 0, right? What am I doing? I'll just do that. And then this becomes 1, 2. Let's see if that works. 30. I just say that. Seven. 61. All right. Now you see it doesn't like the new lines. I don't like it. Could change these to tabs, maybe that will work. Don't like that either. Why does it bring out the new line every time now? We don't have anyway, let's just do that. So as you can see, and then do another note, take that one off. We can now do multiple notes, which is pretty cool. All right, so let's use this and bring this in to our application. How am I going to do this? All right, I am back. We're going to now bring this into our synth. So what we want to do is come up here and include our MIDI. Let's see. Probably will change this to a .h. Try to rename MIDI.h. There we go. So we can now start to clean this up. So I'm going to get rid of this line. We're not going to have the. Don't need S. All of this can stay. This can stay. Now this no longer becomes main. This will be like I'll call this MIDI init, and then you're going to want to pass in a. What was it called? A MIDI key array. Right. MIDI key array. I'll call this keys. Yeah, keys. I'm going to get rid of that line. You're also going to pass in a. Yeah. A device ID and then keys. Call that selected device ID so we can get rid of this one here. So our MIDI handler will be static. I think that should still work. And then it will pass in keys. Well, it's already a pointer, so. And then we can get rid of this application loop. And now we need to have another one, which would be void MIDI stop. believe that's... because the Windows ones, they all start like this, I'm actually going to call this the Synth MIDI. Alright, and then we'll call this the Synth MIDI handler. Just so we know. So, and then this will return a MIDI handle, right? And then all of this line can go in here. This is going to take in our MIDI handle. Okay. So far so good. So now if we try and compile the synth again, included incompatible. Oh, so we have a problem including Windows. Redefinition of rectangle. Once we load that first, error result undeclared. Selected device ID. Well, our MIDI handle is just this. Can we go to that? We might have to go back to our documentation. To our HM. Where can I get information on that? Come on. I think instead we just won't print that information for now. Right. So we've got this problem of redefinition of rectangle because we're including Windows.h. How can we Raylib 218? And what's the Windows rectangle? what exactly does it need? I believe it just needs the Win32. Oh, what was it? Type def uint version. See if that works. Or why is it not working? Error expected. System.h. Can we go to this? Where is it? Where can I find that? What's it saying? 27? Type def uint version. Guess because it doesn't know what a uint is? Oh, so do I need to like do uint? Let's see. And we need to do type def. Yeah. Unsigned. Yeah, that's still just a D word. What on earth? Yeah, but where is it? Yeah, if I do system.h, will it let me go to that? Doesn't go to it. Oh, Raylib TCC include WinAPI system. I don't know why I didn't just read that. Alright, let's have a look for it. C Raylib TCC WinAPI. Include WinAPI system. Alright, we'll just open this with a good old VS Code for now. So if we go to 57, guess it just doesn't know. We should really be including Windows, but I don't know why I'm doing this. That's really annoying. Let's see if anyone else has solved this problem, because I'm guessing other people have used Raylib. Raylib rectangle Windows.h. So probably this might be able to help us. Why is that so big? How do I make it not so big? No. So let's create a new file. We'll call this custom windows.h. And we'll just paste all that in there. Notice it already includes system, which is cool. So now what we can do is just get rid of all that. And then say include custom Windows.h. And let's see. And then if we come back to our synth, I don't know if we want to load this afterwards. No, it works. Okay, we got there. We got there. So move that over there. So we have our MIDI and here. So what are we going to do? So let's define, we're going to have our keys. So it's called a MIDI key array, and we're just going to call this the MIDI keys. So we don't want this anymore. And it's just going to be the count. It's going to be the polyphonic count. And then if we come down to our main function, what we're going to do is when we init the audio device, we're also going to do synth MIDI init 0, and we'll pass in our MIDI keys. So if we peek at that, we'll see, yep, synth MIDI init, and that takes our MIDI key array. And that's going to return our MIDI handle. We'll just call that MIDI. And then before we close that, we'll do our synth MIDI stop. And that'll just take our MIDI. Cool. And now if we come up to our Draw UI, where we set the frequency, we no longer need to do it on the keyboard, so we can get rid of that. What we can then say is if our MIDI keys dot, the first key is on, we need to get the MIDI note number for, where's my, what is the MIDI note for A4? So A4, 6, oh, yeah, nice number. Okay. So our semitone then will be our MIDI keys. Again, we're just doing a monophonic for now, dot note. Minus the base MIDI note. And that's going to be a float. our bass MIDI note becomes this. That really should go in our MIDI. Let's give this a go. So get my little keyboard, get a sine wave. So this is pretty cool. Let's add some more shapes. Maybe rounded square. Nice. So there is a little problem. Even though it's monophonic, I have to let go of a key before we get another one. So one way we can handle that is we could just, if we go back to our draw, is we could do a loop and just find the first note that's on. So this becomes for I is less than MIDI keys dot count A plus plus, and then we'll just say if MIDI keys dot data I is on, and then we'll break. So let's get square wave. Oh, it's not quite working how I expected still. I equals 0, I is less than MIDI keys of count 0, 0. Oh, we need to then say get that. There we go. So now I can, like, if you can see this on camera. Oh, it was working just a second ago. Maybe it's not working. I swear it just worked. Oh, I think what we have to do is go in reverse order. If we want to do that, we just change this to this to go in the list in reverse order. So, because every time we press a key, it appends it to the array. So you want to look in a reverse order to get the most recent key press and play that. So I shall square, make that. There we go, that's working now. Slight problem, which is when we're not pressing anything. So let's see if we can fix that. If we're not pressing anything, this should be 0. So what we could do, save note. You know what, let's just print it. Printf percentage 0.2f. No frequency. Let me get the console. Can I go to the bottom? And run that. There we go. And we bring this here. So you can see it's returning a number, which it shouldn't do. So if we come to this, which means this is one of the keys are on when they shouldn't be. So I'm just gonna comment you out, copy you, and I'm gonna say note on, and then I'll show in the index, which is just going to be I. We'll run this again. Don't do that. -2. What? What? I'm just going to MIDI keys that count -1. No IDX. No IDX. Why? Setting up the MIDI keys, polyphonic count is 16. So, like, if we print the MIDI keys dot count, count. No, you're still. There we go. 16. And then if note is greater than or equal to 0, what? That is equals 1. What on earth? Very bizarre. Is there something wrong with my type? Why is it going to -2? I'm really confused. Like, this is the only place I'm using that type. That's bizarre. What am I doing wrong here? Just a second, just a second. Let me just write this out. Like, if I did int I equals 10, and as long as it's greater than or equal to 0, I minus minus. And I'm going to printf percentage %d I. That should print 10 to 0. Comment out that line. Right. I'm like, I was using U32 before, that should be fine. What? It doesn't like U32 for some reason. That's just an unsigned int. There's nothing. There's nothing special about it. Something really strange is going on. Whatever. So this should be just in. I'll have to investigate that off stream at some point, because maybe there's an assumption I'm making about the language that is just wrong. So let's build it. Sawtooth. So yeah, now that I'm not playing anything, you can see that frequency up here, the fundamental is 0 when I'm not playing anything. Though, oh, I need to set the... So yeah, now you can, oops, sorry, now you can see. Alright, so yeah, that's looking good. Let me come to my about. So we've done that. We have now the ability to play notes. We did it first on the keyboard and now we've got it on our MIDI keyboard. So probably next time I want to do bring him back in the LFO. So that's frequency modulation, and then at some point we want polyphonic MIDI, because we've already got that set up in our MIDI header file, so we actually need to make use of that information. So I'll do that in the next episode, which will be episode 7. See you next time.